Hello everyone, my name is Joe Lee and I'm currently running the ELEC2134 Crash Course. Now, here's the thing, I did run a crash course in person today, but unfortunately the audio wasn't picking up properly. So that means I have to re-record it so everyone can see the best quality I can offer them in a short amount of time. Now, my microphone is not the best. You can probably hear a lot of noise, but hopefully you can at least hear me. Okay, so let's go through everything that I have here. So, quick thing about my color convention, I love to use blue as time domain and red as frequency domain because they make me cool. Let me just pick up thickness. Hopefully you guys can't see this. Okay, so let's get started. So now, the first thing I want to do is the color, the activity. So if the current goes in like this, we know that this side is going to be positive and this side is going to be negative because if current goes into the dot, the other side of the dot will turn positive. You can't think of it like a Mortal Kombat thing where the current goes in here, the current will always come out in the other side of the inductor in the other circuit. That will cause this to be positive and this will be negative because the current flows from positive to negative. That's kind of the way to remember it. You can also do the current, if the current goes in here, you can't imagine the current have to go all the way through the inductor and out here. So if you do this, you get positive here and negative here, which all lines up. So this is one way to remember, and I like to use this method to remember. So let's go down into this question. Sorry. Okay. So find V0 in the time domain. Okay. Let me pick up thickness. Maybe yellow. Okay, so in the time domain, first thing we want to do is to convert these time domain things into the frequency domain. So calculation will make our life a lot easier. 4 ohms will become 4 ohms in the frequency domain, same as 10 ohms. Now 0.4 Henry is gonna turn into the frequency domain. You just need to do J omega L. Omega is 20, L is 0.4, so what you get is J8. J8. Same for 0.5 Henry, you get 0.5 times 20, which will be J10. And you have to do the same to mutual inductance. 0.2 times 20 will give you J4. Hopefully that makes sense. Now, let's do mesh analysis here. We have I1 and I2. Sorry guys, one day I will try to get a better microphone or improve upon my one. Now we have two meshes in mesh 1, in I1. We can deduce that by the way, sorry, I forgot the source. The source has to be in frequency domain as well, which is 150 with the phase of 0. So doing KVL, you do 150 plus I1 times 4 plus I1 times J10. And don't forget the mutual inductance. Sorry, I made a mistake. 1 second. 150 equals to I1 times 4 plus I10 times 4, I10 times I1 times I10, J10. And don't forget the mutual inductance. Remember the current is going in like this. So we know the positive is going to be on this side, negative is going to be on this side. So we can kindly add J4, I2 times J4 because we always care about the mutual inductance. J4 is the mutual inductance over here. J4. Cool. Now, cool. Let's polish this equation a little bit. 150 is going to equals to 4 plus J10 times I1 plus J4 I2. Hopefully this makes a lot of sense. Now let's look at the other equation, I2. In the other mesh, we get in mesh I2, we will get 10 ohms times I2 plus, actually let me reverse the order just to keep it consistent, 10 times I2, doesn't matter, plus, sorry, I think I'm being silly, I2 times 10 equals I2 plus I2 times J8. Don't forget the mutual inductance. I1 current goes into the dot and out of the dot, which means this is positive. This is current goes into the dot and out of the dot like this. Sorry, one sec. Current goes into the dot and out of the dot. So this is going to go from positive to negative. Oh, actually, I might be mistake. Current goes here. My bad. So this is going to be positive. This is going to be negative. So we will just go ahead and add J4. We add it because the dot convention equals 0. Now we can rearrange this, and we can say this is I1 equals 2 minus 5 on 2 J. Trust me on this one. Just some calculator work. Now we're going to go ahead and solve this and find I2. So substituting this, let's call it equation 2. Substitute it into equation 1. We will get 150 equals 4 plus J10. We just replace I1 with this, so I'm going to replace 2 minus 5 on 2J times I2 plus J4 I2. And just another calculator work. We will end up with 33 plus J14 I2. Now we can throw it to the other side of the equation. We will get I2 equals 4.18 to the face of negative 0.401. Now the voltage is going to be current times the impedance, which is 10. So we can go ahead and say V2 equals 41.8 to the same phase. There's no capacitor and inductor. So transferring it back to the time domain, which I will use blue for this. In the time domain, this is going to equals 41.8 times cosine of 20t minus 0.401. That is our V2t in the time domain, V0t. We can call it V0t. V0t. Let's call it V0t, just to make it look cooler. Okay, now we have our first question done. Instantaneous energy. So as I said earlier, I2. We already have an equation for I2. Now we're doing this one for the moment. I2 is going to be equals to 4.18 with the phase of negative 0.4. This is calculated beforehand over here. So pretty simple. I'll go ahead and erase this. Now transferring it to the time domain, we already know what will happen. We can just straight up pull out this equation, 20t minus 0.401. Now let's do the other one, I1. I1, we can simply use equation 2 over here. So equation 2, what will we end up with? We'll end up with 2 minus 512j plus times the I2. We already have them, so we just need to chuck it into our calculator, and we'll end up with 13.40 with the phase of negative 1.3. Cool. Now, in the time domain, this is going to look like I1t. You could simply just say 13.40 cosine of 20t minus 1.30. And substituting 2, because we only care about at time equals 2. So I1 at 2 is going to equals to, substituting 2 into this equation, and this equation, I12 is going to equals to 7.23. I22 is going to equals to negative 1.35, sorry, negative 1.35. Hopefully that makes sense. Okay. Now, using the equation we have on the left, we know the energy, omega, is going to be 1 on 2 L1. What is L1? L1 is 0.5, and L2 is 0.4, and M is 0.2. So we can simply substitute our value, chuck them all into this one gigantic equation. L1 is going to be 0.5 times I1, 7.23 squared, plus 1 on 2, 0.4, I guess, 0.4, multiply it by 1.35 squared. It's negative, but negative squared is just positive. And then now, at plus or minus, the current is going into the dot in both scenarios. I2 is going into the dot, I1 is going into the dot. So if both is going into the dot, then I1, I2 is positive. If either one of them is going out of the dot, only one of them is going out of the dot, then this will be minus. So in this case, it's positive, so we can just go ahead and add them. Because both current is going into the dot, we can just add M. M is 0.2 times negative 1.35 times 7.23. This will give us a final value of 11.48 joules. Cool, happy with this. Now, let's find the coefficient, coupling coefficient. Coupling coefficient can be found by M divided by square root of L1 times L2, which, if you substitute all the value, you should get 0.447. Now, what is this number? This number tells us how much coupling is happening. So if this number is like 0, basically it means there's no coupling. Like you can see M is going to turn to 0 if K is 0. So there's no coupling. The inductance are independent. If M is 1, it means this is an ideal transformer. And if K is like this much, it means energy, they kind of not fully current is not fully induced to the other circuit. Now, speaking of ideal transformer, let's move on to ideal transformers. I'm sure a lot of you have done physics in high school. You've probably seen this like so many times. This is the equation for ideal transformers. Now, we can derive a load impedance over here. So let's kind of look at this. Load reflecting. So if we look at this part, it's called the reflected load, ZR. What is ZR? What is ZR in terms of Z2? Okay, so we can first say that ZR is equals to the current going into the coil. Sorry, voltage divided by current. Coil. Sorry, maybe I should use coil. V1, I1. So V1 is just this one. I1 is just this one. The direction doesn't really matter over here. We just care about the load, the impedance. So V1 over I1. Now using this equation over here, we can derive. Let me use green. We can derive that. 1 second. N1 divided by N2 multiplied by V2 whole thing divided by N. This is from above equation, the equation above, divided by, you can express I2 in terms of I1 in terms of I2. So the bottom is going to be N2 divided by N1 times I2. This come from here, this come from here. Now simplifying this, you will end up with Z2 divided by N2 on N1 squared. So what will you get? So now for 1 over 1 to n, so when n1 is 1 and n2 is n, we will get reflected. Ooh, that's a heart right there. Nice, thank you. Don't need it right now, but appreciate it. Z2 divided by n squared. So that's kind of a method to reflect our load into the secondary coil circuit. So let's go down here and have a look. Ooh, okay. Sorry about this. Now reflecting this looks tedious, but don't worry. First thing we need to do is reflecting this into here. 1 second. First thing we need to do is reflecting the right coil circuit into the middle circuit. So to do that, reflecting 60 minus 50 on J, we will get 60 minus J, 60 minus 50J divided by 3 squared, which gives you 20 on 3 minus 50 on 4, 50 on 9, sorry, 50 on 9J. Now we can just kind of, let me just quickly draw the illustration. We can just kind of boom and delete this part, and this new load is gonna be this one. Okay. Now add 16 to that. I'm gonna change the color. Reflect. Now we reflect reflect this whole circuit into this part, reflecting 20 on 3 plus 16, which is going to be 22.67. So reflecting 22.67, which is 16 plus this, minus 15 on 9J. Now reflecting this will give, you just need to divide by 2 squared. 50 on 9 we can just write in decimal point because that makes life easier. 5.57J divided by 2 squared, because n is 2 in this case, we will end up with 5.7 1.67 minus J times 1.39. Now, adding the total impedance, we'll just add these two to it. Total impedance. So if we add 6 minus 4J, we're going to get 11.67 minus 5.39J. Now, to find the complex power, first we need to find the current. The current is simply just the voltage divided by the total impedance, which turns out to be, chuck in the calculator, we'll find out it's 4.24 plus J times 1.96. Now, the power, let me use yellow. So you end up with power equals to V times I conjugate. Chuck it into your calculator and you will find out 254.3 minus J11 117.5. That will be your power. Okay, we're done with this part. Now, transient analysis, a very cool feature. Part about transient analysis is you get these different second order differential equation that behaves in a new way. Now we have to solve this question. Consider a above circuit with this, and this, with a step function 5ut. Find the expression for v0 in terms of t. Now second order differential equation, we need to find it. To find it, really easy, don't worry. So we just need to do a current here. This is called IL. Let's call this IL. This is IR. So it's basically V0 divided by R, because this entire node is V0. Now the other current is going to be IC. And the cool thing is, I can actually drag them all the way down here, because that's where I'm meant to draw it. Sorry about this. Now, cool thing about IC is IC, you can kind of derive it. IC equals C dV naught dt. Another equation is called inductor one. It's VC equals L di dt. DIL dt. Okay, very important. I want to say this is VL. VL equals L di dt. You know why later. So to form the second order differential equation, you just need to do a little nodal analysis over there. IL equals V is not on R plus L C d naught V naught dt. Now we don't like IL in here, so we want to like make in terms of voltage. So let's do that. Deriving both sides, let's derive both sides. So I'm going to add L times 1 and L here, because you'll see why later. Maybe 1 L times L. Now deriving both sides, you get d on dt times IL equals 1 on R times dv naught dt plus c d square v naught dt square. Now this magical box is going to turn this whole thing into VL. So this turns into VL, which is this is VL, okay? But VL is not V naught, but we want stuff in terms of V naught. So VL, we can kind of write here, VL is equals to VS minus V naught. This is what we know. Vs is here minus V naught is here. Cool. So 1 on L. 1 second. 1 on L Vs minus V naught equals C d squared d squared V naught dt squared plus 1 on R dV naught dt. Now if you try hard to rearrange this thing, you will get something like this. Vs on Lc equals d squared V naught dt squared. I rearrange. We don't want any constant. We don't want any term here except for 1. Plus 1 on Lc dV naught dt plus 1 on Lc V naught. Cool. Happy with this, hopefully. Now we have our equation. We're technically done. Like, all we have to do is solve this equation. That's all we have to do. So let's attempt to solve it. This is our equation that means everything. Now, our second order differential equation should look like this, and we have this and this here. I'm gonna copy this for later. So we have this. Now I'm gonna explain each term. The first term is alpha. Alpha is called the damping factor. So I really want you to know this. Damping factor, actually listen to the name, damping factor, how much you're damping it. I'm gonna explain this in a moment. Omega n is called the natural frequency. So the frequency before you damp it, like this, the sine wave that you're damping, natural frequency. And omega d is the damped frequency, the frequency after you damp it. Cool. Hopefully everyone's happy with this. And omega d can always be found by square root of the magnitude of omega n squared minus alpha squared. Can always be found like this. Now, in our equation, which I have here, I'll quickly drag this out in the front like this. We know alpha, 2 alpha equals 1 on LC. So alpha is going to equal to 1 on 2 LC. Which is, if you chuck everything, plug in the values R and C, you will find out that this is actually 5,000. For omega n, you get 1 on square root LC because omega n squared equals to this. So omega n equals 1 on square LC, which you found out it is 31623. And I'll give it a unit radians per second in frequency. And we also end up with 1 mole damped. So in this case, it's going to be square root of omega n squared minus alpha squared, which is going to be 31225. Again, radian per second. Cool. Now I'm going to explain what alpha, omega n, and omega d means. So omega n is the natural frequency, the frequency before you damp it. So this sine wave, the frequency of this thing is omega n. Now, what does damping means? So let me grab out my colored pen. Actually, let me add a pen, add a green color. Okay. So damping means you push the signal down like this. Ooh, you push it down. So alpha is determined determines how hard you damp it. If you damp it really hard, you can damp it really hard, the signal's gonna end up looking like a bell, like a curve. If you don't damp it enough, you damp it like a little bit, a tiny little bit, the sine wave's gonna end up looking like this, and it's gonna go lower, lower, lower. But it's gonna still gonna oscillate that. Okay, and I'm gonna quickly address these. So if alpha is greater than omega n, means the amount you damp it is greater than the wave itself, the wave, the frequency. You're getting an overdamp response, so your signal is gonna like woo. So you damp it way too much, so the sine wave is completely just gone. You can't see the sine wave, the wave anymore. Now for underdamped, you don't damp it enough. You like the damping factor is less than the natural frequency. So natural frequency, you damp it a little bit, So if you don't damp it enough, you're gonna get something like, ooh, it still oscillates, but yes, it's gonna get lower and lower, lower. Now critically damp means you damp it just enough to make it such that the sine wave just disappeared. It doesn't oscillate anymore. So you're gonna get a really flat curve here. Now what happens at alpha equals 0? Okay, if you think of this in terms of word, it means damping factor is 0. You're not damping it at all. You will get, what would you end up getting? You will get this sine wave, and yes, you get the sine wave, and undamped sine wave that oscillates forever. Now, after I explain this, we can go ahead and look at this. Our alpha is 5,000. Our omega n is 31623 radian per second. So our damping factor is less than the omega n. So let's look at this. Alpha is less than omega n, which is underdamped. We know our response is going to be underdamped. Let me mark a star here. Oops, sorry. Now you can solve it like this, just using finding the two roots. You can find the two roots and find this, but you end up having to solve a big math equation in order to get something as nice as this. You get complex exponentials, and you can kind of form like something like sine theta equals to e to the j theta minus e to the negative j theta on 2i. You can do this, but it's gonna cost you a lot of time, right? We don't want that. So if you want to do it really quickly, especially in exam, you always want to do exams really quickly. I would recommend using method 2, which is probably the normal method to do it. So again, underdamped is when your damping factor is less than the natural frequency. Overdamped is when your damping factor is greater than the natural frequency. And critically damped is when the damping factor is equals to the damping frequency. Just saying it in words so you can kind of memorizing it. So using method 2, we know omega n, which is 31623, is larger than the damping factor, which is 5,000. So our response is underdamped. And we can write our response like this, our natural response, which in this case I'm going to put Vn, natural response. I could just could really love to copy and paste. Sorry about this. Bad handwriting, but you get my idea. I was drinking water. Let me improve this. Omega D can be improved. Whoops. Okay, hopefully this is good enough. Basically, I just yoink it out of here. Cool, everyone happy, hopefully. Let's go down. Now we need to find a solution for forced response. Now, we have these green one, they're probably not going to appear in the exam. This came from Math 1B. So you kind of have to guess a solution for the forced response. So what do I mean? So we have our differential equation. Let me just pull it out here. We have our differential equation here. Now, what values of V0 should we put in to make the right hand side equals to the left hand side? Really simple. Let's look at what our guide to guessing is. So polynomial with degree n. We currently have a constant term, which technically a polynomial with degree of 0. So we will have to guess for a constant as well. So our forced response is a constant. If this is a constant, now we have to guess for a constant. What constant will we put in V0? So if we put in V0 equal to K, a constant, derivative of a constant is 0, derivative of a constant is derivative of so this 2 will just become 0, and you get end up with V0 on LC. Now, Vs is 5 UT. So a really strategic method to find V0 is just V0 equals 5, because Vs is 5, so V0 is 5. Yeah, kind of. Yeah, that's not too hard. You just kind of eyeball it, which is quite direct, because you get V0 on LC equals Vs on LC. So if Vs is 5, V0 is 5, right? Cool. Complete the solution. So now we have our natural response, which is here. Sorry, this is forced response. Let me just put it. Forced response is 5. Natural response is this. And I'm going to go ahead and do the lazy work. Oops, sorry. Yes, I'm going to put it here with the natural response. This is the natural response plus the forced response. Forced response is 5, so there we go. This is our complete solution. Now we have some constants left in this equation, so we need to find these constants, which is the next part. The key to finding constant is to use capacitors and inductors. What's so special about them? Well, because the voltage across the capacitor doesn't change instantly. 0 minus is going to equals V0 0 plus, because the voltage across the capacitor, which is this one, doesn't change instantly. So this is going to equals to 0, because before the step, this is 0 volts, and everything in here should be 0 volts. So this is going to be 0 because of C. Yes, because of C. Now V0, so we get one equation nailed down. It's going to equals to e to the power of negative alpha 0 times B1 cosine omega d. What's omega d? I don't know, but I don't really care because it's okay. It's turning into 0 anyways. Plus B2 sine omega d times 0 plus 5. Now cosine 0 is 1. We get e to the negative 0 is 1. So we get B1 Sine 0 is 0, and then we get plus 5. So 0 equals, so we end up with b1 equals -5. Now, once we get b1, we can go ahead and keep going. Now, the inductor is the other thing we use, but the inductance is, we don't really care about the voltage across the inductor. We care about the voltage across here. So what can I say? When the voltage steps up, inductor current doesn't change instantly. That means the current through here and the current through here doesn't change instantly because it's stopped by the inductor. The inductor causes them not to change instantly. Cool. So because of L, which is the inductor, the capacitor current doesn't. Okay, the capacitor, if it wasn't for this inductor, if this inductor doesn't exist, then the capacitor current can change instantly. But right now there's an inductor here stopping the current from here from changing instantly. So because of L, the current through the capacitor does not change instantly. So IC 0 minus equals IC 0 plus. Equals, what's the current through it? It should be 0 because there's no current initially when the voltage source is just 0. Now, here's the nightmare part, which is not really a nightmare, don't worry. We have to derive it. Equals C dV dt. And deriving this equation will bring us a really funny chain rule. So what, can I quickly take this chance to write down the, actually 1 second, let me write down the equation so life will be clear. At this point, V0 t equals to e to the negative alpha t times B1, which we found is -5, -5 cosine omega d t plus B2. B2 is what we're looking for. Sine omega dt. By the way, I want you to notice how this is omega d, damped frequency. So now that we damp it, it oscillates at damping frequency because this is a damped signal, right? We look at these two, omega d. So the signal looks like this, and the frequency is omega d. Okay, now in deriving this, we end up with some chain rule magic. We get we first integrate the exponential part, e to the negative alpha t minus 5 cosine omega d t plus b2 sine omega dt. And then we derive the other part, chain rule, classic chain rule moment. Deriving cosine will give you sine 5 sine omega dt, negative sine, and deriving sine will give you cosine. And also don't forget the omega d inside. We kind of have to chain rule it out. Oh, sorry, this is not the chain rule, this is product rule, my bad. This is chain rule, this is product rule, my bad. Now, substituting t equals 0, what we'll end up with C0 equals to C times negative alpha times -5 plus B2 times omega d, because note all the cosine just turns into 1, sine turns into 0, sine turns into 0, cos turns into 1. Now we can then deduce that B2 is negative 0.8 if you substitute all the alphas and omega d's. And finally, we can write out our final line of working, which is what the question asks for. E to the negative 5,000, which is alpha t, like an unravel the event moment, negative 5 cosine 31225, which is omega d, t minus 0.8 times sine 31225. And believe me or not, this is actually correct. And if you don't believe me, just plot it in FT Spice, you get the exact same graph. Exact same graph. Okay, hopefully everyone's happy with this. Now time to talk about my favorite part of ELEC2134. It's called the Laplace transform. Now, so for starters, this is the Laplace transform equation. There is an inverse Laplace transform equation, but you won't be able to know how to do it unless you did Math 2069, Math 2B, no, that Math 2A, sorry. And you probably won't be assessed in this, so don't worry about this. This green stuff, you can ignore this. Now let's start off by finding the Laplace transform of this using the definition of Laplace transform. So I'm going to do a little bit of show time here. Again, I want to use blue as frequency as the time domain, ft. Now Laplaceing this, you have to do the integral from negative infinity to infinity e to the alpha t times ut times e to the negative st. Now, we only care about the unit step function. So everything before 0, we don't care about. Please recall that unit step function looks like this, where you before its life begins, it stays at 0, but after that it goes to 1, like this. Now, so that's why we can just ignore all the negative part, because it's just 0 anyways. So you would get something like e to the negative alpha plus st dt. And I'm sure everyone knows how to do integrals, so I'm gonna go ahead and integrate this. Integrating exponential will give you something like alpha plus s. I think the negative should be somewhere down there. The negative should be here. From infinite to 0. Now, you will end up with 0 minus 1 over minus alpha plus s, which will give you your equation. Cool. Now, one moment. Let me quickly upload. Okay, so you know how doing this Laplace transform by first definition, it's quite tedious. So that's why we are given formulas, which makes our life a lot easier. By just looking at it, we can derive the Laplace transform. Okay, so for now, let's kind of pretend that this doesn't exist. This equation doesn't exist, because I really want to bring you through it. Let's just remove it. We'll erase it later. Just at the time being, just pretend it doesn't exist. How would we solve this question? Now, first of all, we know the Laplace transform of a sine wave, sine omega t. If you take the Laplace transformers, you will get omega on s squared plus omega squared. Why do I know this? Because of my formula sheet. My formula sheet says sine omega t Fourier transform will give omega over s squared plus omega squared. Cool. Now, if I have an exponential e to the negative alpha t ft, if I take the Laplace transform of this, I will end up with the Fourier transform of the same function, s plus alpha. Why do I know this? Again, because the formula sheet says this. The formula sheet says frequency shift e to the negative alpha t ft times will give a Fourier transform of f s plus alpha. Okay, now if we let ft equals to sine omega t, we can kind of say e to the alpha t sine omega t. This will bring a Laplace transformation of fs plus alpha. So fs is this, fs plus alpha should be replacing all the s with s plus alpha plus omega squared, and this will be our final answer, which is exactly what the formula sheet has here. See? You can actually derive this instead of like showing. Now find the inverse Laplace transform of this thing. So this is a little bit tricky, but we can do this. First, we start in the Laplace domain. We don't like the bracket like this because we really want to separate it. So let's expand it. S squared plus 2s plus 4s. The reason I'm expanding it is because there's no equation. There's no way I can separate these products, and there's no equation that can really help me in here. So let's separate it now. Divide by s squared plus 3 squared. Cool. Now I can take out s squared plus 3 squared, which is s squared plus 9. So I will end up with 1 plus 6s minus 1 over s squared plus 3 squared. Okay, now looking at the right fraction, what looks the most like this one? I think the equation that looks the most similar to this one should be sine. Actually, no, it's cosine because s cosine x s times a constant, cosine theta is a constant, minus a constant. Okay, so let's go back to this. So we kind of want to try our best to, let me just screenshot this so we can refer to it. Screenshot cosine and then put it here. Whoa, whoops, my bad. It doesn't really like me. The cosine doesn't really like me. Put it here. Now, s squared plus 3 squared, s6s minus omega. What is omega? Omega is 3 apparently. So, yeah. Okay, I can kind of let 3, pull out the 3 here. So first we're going to form omega, which is 3. So this is going to be 3 times 1 over 3. Now we have omega. Omega times s cosine theta. So we need cosine theta here. So 6, we have 6 here, and 1 over 3. So this is going to be square root 6 squared plus 1 over 3 squared, which plug it into the calculator. Sorry about that. Ooh, sorry. Hopefully it didn't scare anyone. You get something like square root of 36.11111, which is basically 6. It's basically 6.001. Divide both of them by this. Divide both of them by this. 6.0061. You will get, so if you try your best to kind of put this outside, I'll quickly lasso it out there. Sorry, let me try again. You get square root of 36.1111. So now what you get inside the numerator? So this is theta. You get 6 divided by square root of 36.1111. That is cosine theta in here. So cosine. So we get s cosine theta minus 3 times 1 over 3 divided by the hypotenuse, which is sine theta, s squared plus 3 squared. Pretty cool, right? Now we can, sorry about this. Now we can go ahead and inverse Laplace transform this peacefully. We need to know what theta is. Theta we can easily calculate by arctan 1 on 3 divided by 6, which gives us probably a near zero angle. 1 on 18, 3.1718 degrees. So we can inverse Laplace transform it. We get ft equals Laplace transform of 1 is just dark delta. 1 on square root of 7. You get square root of 36.111, and you get cosine of omega t plus theta, which is 3.18 degrees. Okay, hopefully this makes sense. Let's move on. One moment. Now the same question as before in the step response, but this time we want to find it with Laplace domain. So the inductance in Laplace, let me quickly draw it down with a light green. This inductance in the time domain is 10 millihenries. In the frequency domain, it is 0.01 s because in the frequency domain it's L times S. So L is 0.01 times S. This is what you get. So yes, that's good. Let me just try to decrease the thickness of this thing. Now the resistor has a resistance of 1k ohms. In the Laplace domain, the resistance should not change. It's still 1000 without any S. And the capacitance is in the time domain, it is 100 nanofarad. And in the frequency domain, you use 1 over Cs, you get 1 times 10 to the 7 times 1 on S. Now, to find V0 is this one. In the Laplace domain, V0, this is V0, let me just label it V0. you need to do a voltage division here. So you can just simply go V0 S. It's going to be the source. Oh yeah, also the source. Let me just label source. Source is 5ut, right? 5ut. In the Laplace domain, if you do a Laplace transformation, you get 5 on S. And then you will get something like 5 on S here. 5 on S. Do a voltage division. Multiply by 10 to the 7 times 1 on S. In parallel with 1000. And then divided. This is a voltage division. 10 to the 7 times 1 on S in parallel with 1000. And then add that with the inductance 0.01 S. Okay. Now hot tip, you do this a lot. So 5 on S here. And then we can have inverse 10 to the 7 times 1 on S. Now I'm gonna quickly inverse it. If you inverse this, you get 10 to the negative 7 S plus 10 to the negative 3. And you can kind of have this. Yes. Now I don't like inverses in my equation because they make my equation look ugly. So I'm going to go ahead and times numerator and denominator both by that big chunk of thing. So now my top part becomes 1. Oh wow, this is S by the way. S. This will become 1 and this will become 0.01 S times this, which will bring you 10 to the negative 5 S plus 10 to the negative 9 S. And if you try to like make this look the absolute best fine condition, you will try to make, okay, this is S squared by the way. You will try to make S squared a term of itself, and 10 to the 4 S and plus 10 to the 9. And then this is 10 to the 9. And there we go. That's our answer. If you try to inverse Laplace transform this, you will get the exact same answers we've got before, which is pretty cool. Okay, Laplace transformation. Let's look at plotting on the S-plane. Now, if you look really hard, actually no, it's okay. You don't have to look really hard. Right, so let's simplify this because I don't like looking at this big bulk of thing, really ugly, and I want to like make it into brackets so I can like easily see where the poles are. So let's go ahead and separate it. S squared plus 6s plus 25. Do we have to do 25? We can't. Okay, first of all, I think we can't really factorize this because, yes, you can try. You can't really, but you can if you use complex numbers. So here's how we do it. Note how all the terms are real. So let's make this square, sum of square. This will be s squared plus 6s plus 9 plus 16, which is 25. This you just separate 25 to this two, and then just do some math work. It's a really useful math trick that everyone can learn. S plus 3 squared plus 4 squared. Now, this is essentially the sum of the product of two complex numbers. So you get s plus 3 minus 4j s plus 3 plus 4j. So this is essentially the sum of product of differences, okay? Now, plotting this, let's plot the zeros first. We can see two zeros at s equals -2, so let's plot it here. -2. You can label a little 2 here just to indicate there's two zeros, sorry. Now the poles is going to be 1 at -3 plus 4i, which is -3, -3 plus 4j, sorry, j and I is the same thing. A pole is indicated by an x, and also another one here, which is -4j. Another pole here. So we have two poles. Ooh, it doesn't look really, but you get the idea. -3 minus 4j, -3 plus 4j. So two poles and two zeros. Drawing activity. So I kind of want to like show everyone a little bit of artwork. So if we plot this in a three-dimensional graph, so this is just the top view. You'll be asked to do this in the exam, but you will not need to draw a three-dimensional S-plane in the exam. This is purely just for me to show you how it looks like actually, and you can have a better idea of plotting a transfer function from this. So just copying the previous from the top view, we get two poles here and a double zero here. Now, what happens in a pole? The pole goes to infinite. So basically, whenever s is equal to -3 plus 4j, this goes to undefined, really high undefined. So it just goes to really high. And this one as well, it goes to infinite high. I'll try to sketch it. Now, so I'm gonna try to like make it look nice and clear. Right. Hopefully this will make sense. A little pole. It's like a little thing that goes up like this. So this will go a little bit down. Let me just completely draw this. Again, I will like repeat myself. Do not draw this in the exam because you'll waste up all your time. Draw this in your own time for fun, but don't draw it in the exam. Now, there's another pole here, so I'm going to draw it. A little artwork section. Hopefully everyone will enjoy watching me drawing this thing. Okay, I'm going to try to reshape this. This is what happens in the pole. This goes to infinite. I'll show you the elegance about this and the importance of why am I showing you this. There's a reason I'm showing this, and for a good reason, just to help you visualize stuff a little bit better. Oops, sorry. Maybe you can go like this. Don't have to draw too detailed. And what happens in the zero? In the zero, stuff sinks down into this pit hole. It sinks down. Just whoop. Whoop. It sinks down. Let me just keep drawing. Sorry. It sinks down like this. Sinks down like this. A little pit hole. Okay. I'm trying my best to like draw a general shape so I can later show you what's actually going on. Okay, so you get a little plane here that is risen up by poles and sunken by zeros. You kind of get this dragging down all the plane. Okay, so what happens is on this graph, let me just quickly reshape this. What you get is on this graph, you kind of get this little intersection where you kind of shape by something like these. Okay, see how there's like a little pit in here? That's because of this pole, this zero, kind of like dragging the entire plane down, and then there's like maximas here because of this pole dragging everything up. So that's the elegance. So because the next question is going to be, now roughly sketch the transfer function. So so basically we can just copy the y-axis, the plane over here, this plane. Let me just quickly illustrate it here. We're just drawing this plane. This plane, okay? We're drawing this plane. So we just need to draw this plane here. It's a rough sketch, so it's not exactly right, but you kind of get. Sorry. You get a rough sketch like this. It goes up a little bit. It goes down. And then on the right side, you got the same thing. You go up a little bit and kind of match down. A little key features of this is the plane kind of lies about 4 because, why is it 4? Because this is 4 here. The gain is 4. That's why it's 4. And the maximum location is about, let's look at this. It's about, so I'm looking at the top view. It looks like it's about 4i and negative 4i. So this is kind of like 4i. It's like negative 4i. So we can put that here. 4i. We don't need the I here. This is just omega. And this is going to be negative 4i, which is negative 4 here. And then, yes, that's kind of our vibe. Hopefully this makes sense. A roughly sketch, so we don't have to care about it too much in detail. Hopefully this makes sense. A little illustration just hopefully gives you an essence of Laplace transform on a plane. Now let's do this extended question. Now we have s plus 3. We can quickly put s plus 3 down because we love it, but we don't love the next one, which is s squared plus 4s plus 13. So let's kind of try to make it look better. Plus 4 plus 9. Divide the whole thing by s minus 3. We also don't love this one, so s squared plus 3s plus 9. Wait, do we plus 9? Oh wait, I think I made a mistake, but it's okay. Can we change the question a little bit just to make our life a little bit easier? This changes to 6. 6s plus 9, sorry about this by the way, 6s plus 9 plus 25. I made a mistake while making this question, sorry about this. Times s plus 6. Now, again, we can quickly Avogadro this thing into s plus 2 plus 3i, s plus 2 minus 3i, and then they did like you basically like putting them into all brackets. S minus 3, s plus 3 plus 5i, s plus 3 minus 5i, s plus 6j, sorry, x plus, actually no j. Okay, s plus, okay, so let's plot the zeros first. There's 1 0 at -2, which is, sorry, there's no 0 at -2. There's 1 0 at -3 though, let's put it here. 1 0 at -3. At -2, what happens? -2 plus 3i, which is here, we plot 0 here, -2 plus 3j, -2 minus 3j. And this will be 2, -2. Okay, we're done with all the zeros. Now all the poles. S plus 3, apparently it's this side. There's a pole in here, which I'll talk about in a moment. S plus 3, 3 plus 5 is S by the way. 3 plus 5j, I'm going to put it here, a pole here. That's 5, and a pole here. -5. And we have 2 poles and 1 more pole here, s plus 6. Another pole here, -6. Okay, we successfully plotted everything. Is the system stable? Well, the key point is there's a pole in here. There's a pole in the right side of the plane. Okay, so let's think about what it means. So what does phi means? Sigma means. So sigma basically is like a exponential component. So you get phi, sigma plus j omega, which is t, and we get 2 components. We get e to the sigma t and e to the j omega t. Now let's not care about this for a moment. Let's care about this one. Let's care about this one for now. So what happens when sigma is larger than 0? This exponential component will go like whoop, goes up to, it'll keep going upwards and never stop. So that means, like, despite whatever you have on with it, even though if it's a sine wave, it's go like this. It's gonna go like this. It's just gonna keep going upwards and do something bad. So this is not stable. If sigma is greater than 0, system not stable, which means if any pole lies on the right hand side of the plane, the system is not stable. So only if it lies on the left hand side of the plane, that's acceptable. Because if sigma is less than 0, you get the graph looking like this, which is indeed stable because it keeps going down, which is not going to do something bad to our system. Not always, but systems gonna tend to be like, let's not write that down. Let's just say if pole lies on the left side, it's okay. If poles lie on the right side, it's not stable. To add on to that, can we have more zeros than poles? The answer is no, unless you're in a digital system, which you learn in digital signal processing, where you can actually have it's called finite impulse response. You can't have it in analog circuits because you can't physically make them. Okay, next part. 2-port networks. Impedance parameter. One thing cool about 2-port network is you can find a lot of information about a circuit without knowing what it looks like. So let's say there's like a little black box. You have a little black box here, and you don't know what's inside. But you are given, you know the parameters of it. 21H22. Then, since you know this parameter, you can do a lot with this circuit. Like you can get a lot of information out of them. So that's one thing cool about two-part networks, like the parameters. Okay, so let's get started. First parameter I want to introduce is called impedance parameter. So one thing I really love to do is to memorize this instead of this big First thing I want to do is I like to memorize this matrices instead of the big equations like this one I'm about to write. E1 equals Z11 times I1, Z12 times I2. And we can do the other one, V2 equals Z21 times I1 plus Z22 plus I2. These two equations can be derived from here. That's why I like to memorize this. I like to save brain hard drive, okay? I like to save my RAM, my RAM and hard drive. I can't memorize so many stuff. Okay, so with these equations, first we like to let I1 equals 0 or I2 because we want to like get rid of this so we can like calculate Z11 and Z12. First we let I2 equals 0, so no current there. So V1 is going to equals I1 times 30, which makes I1 times 30, which is here, and this current times 50. This current is I1 plus 2I1 because I2 is 0, so this current is just going to be 3I1. So it's going to plus 3I1 times 50. So you will end up getting 180 times I1. So with this, we can derive that Z11 is equals to 180 because this is V1 equals to Z11 times I1, and we have V1 equals to 180 Y1. Now the second equation, we look at this, V2, what is V2? V2 is I1 times 50 Okay, yes, V1 is the current through here times 50, which is, we already established, is 3 times I1 times 50. So V2 is going to be 150 times I1. So with this, we can deduce that Z21 is going to be 150 ohms. Again, this is in ohms as well. Cool. Hopefully you're happy with this. Now, we're done with Z11 and Z21. Let's do it with Z12 and Z22. So we let I1 equal 0. There's no current here. So if there's no current here, that means there's no current here. That means you're only looking at this part is open circuit and you're only looking at the 50 ohms. So let's start with V1. V1 is going to be current I2 times 50 because I1 is 0. There's no current through it. So the voltage across this is going to be the voltage across this. So with this equation, we can easily say that Z12 is going to be equals to 50 ohms. Now the final one is Z22. Now V2 equals to I2 times 50. Again, pretty straightforward. You just go current through here. Current is I2. So you get Z22 equals 50 ohms again. So you get this really nice impedance parameters, which you can express as in terms of matrices. Cool. Hopefully everyone likes this. Now the application of this, well, you can cascade two blocks of impedance two-port networks in series, and you can actually add the matrices together like this. Pretty cool, right? So the impedance parameters of the whole system is going to be equals to impedance of this plus the impedance of this in matrices form. You just add them together. That's pretty cool. Next part, admittance parameter. Same circuit as before, but this time we're trying to find the admittance of it. So again, I love to save brain memory, so I just write this equation down. I1 equals brain num y11 times v1 plus y12 times v2 y21 y22 this is I2. We get two equations from here. Right. Okay. So let's get started. So again, we want to get rid of these two. So we can kind of find y11 and y21. So v2 is going to equal to 0. Let equal to 0. Let v1 is going to be 30i. I1, why is that? You might ask. Because what's v2 equals to? You're essentially short-circuiting this part. So if you short-circuit this part, the voltage across here is 30i1, and then the voltage across this one is 0 because you're short-circuiting it. So with this, you can safely say that y11 is equals to inverse 30 because this says I1 equals to inverse 30 V1. And this kind of match with this. Okay, I'm gonna erase it to save chalk. I can't save chalk, but sure. Now the second one, let's do a little nodal analysis over here. We get I1 here, I1 plus 2I1, which is this current, plus I2. By nodal analysis, this should be equal to 0. You might ask, where's this current? This current should be 0 because this voltage is the same as this voltage. So there's no current going through this resistor. Now 3I1 is going to plus I2 is equals to 0 because we just now I2. What is I2? Well, sorry, it's not I2, it's I1. Now we can find I from the above we know I is equals to 30V, so we can go 30 negative 30 inverse times V1 equals 3I1. So to find I2, the current through is the current going in. Just add them with the I1s, and you get something like y21 equals to negative 10. I think I made some sort of stuff over there. I'm not sure what happened, but let's just assume I'm correct for the moment. Because the answer works out, trust me, because I've did this before. Now let v1 equals 0. v2, if anything doesn't work out for you, or you find a better solution than me, just feel free to put down the comment section, and everyone can see it. So everyone will roast me together. This time we short circuit this part of the circuit, V2 equals to negative I1 times 30. Why is that? V2 is this voltage equals negative I1. We're looking at the current going through here. This is negative I1 times 30, and the other part's short circuited. So we can just go this voltage is equals to this voltage. Hopefully this makes sense. Now we go Avogadro, and now we can deduce that Y12 is going to equals to negative 30 Siemens, inverse Siemens. Now doing the same thing, we can I2 plus 2I1. What is I2 plus 2I1? I2 plus 2I1 would be this current. I2, this current. This is I2 plus 2I1. And now we want to find the voltage across V2. So we have to multiply current by the impedance, which is 18.75. I calculated it from 50 parallel with 30 equals V2. You will end up with I2 equals 3 on 25. You might ask me, why is the I1 just suddenly disappears like magic? Because I1 is, you know what, give me one moment. Because 2I1, ooh, good question, Jolie. Right, okay, sorry, my bad. Let's move this to the other side to make space for our working out, so I can quickly derive this. 18.75 inverse. Now we have 2I1 over here. And we'll quickly change I1 into V2. So this is going to turn into negative 30 inverse 2 times negative 30 inverse V2. And then we can kind of manipulate this whole equation to make this. And we'll end up Y22 equals 3 on 25. Because it's mentioned here, Y22 is equals to I2 on V2. And we get our admittance parameter, which is here. Let's put it here. Now, multiplying this with the impedance parameters, which we got earlier, if you really try to do it, you will find out that multiplying them together will, non-surprisingly, give you 1001. Because the admittance is the inverse of impedance. That's what defines. You can mathematically prove this. I'm going to leave it here. Application. Just like normal circuits, your admittance adds up in parallel. So if you cascade the two networks in parallel, you can find the total admittance by just adding them together. Now, hybrid parameter is definitely what you will see in 2133, ELEC2133, where you learn about transistor. This thing right here is a transistor model. It's like a good estimate of what a transistor behaves like. So let's try to prove this. So let's write out our two equations. Reference to the matrix equation. I'm trying to improve my handwriting. H11 I1 plus H12 V2 it's kind of mixed around. Okay, now first thing we want to do is let V2 equals 0. So what does that mean? That means short this part, short circuit. Now VB, we know V1 equals to HRE VC, because why? Because of this. So VC, what is VC? VC is actually V2. VC means this voltage, collective voltage. Actually, now we shouldn't look at this one. Sorry, 1 second. I'm being silly. Sorry. Let V2 equal 0. I'm being silly. V1 equals to I1 HIE. Why is that? Because I get V1 is here, VC is 0, so this is going to short. This is going to short because VC is 0. So V1 is technically equals to I1 times HIE. So because of this, we know H11 is going to equals to HIE because H11 times I1 equals V1. Now, the next one, HFE, we're targeting FE. So HFE times base current, which is IB, equals to I2. Why is that? Because this part is shorted. Now, because this is shorted, the current is not going to go through this resistor. So it's going to go through here into this short circuit and go through here. So I2 is going to equal to HFE IB. So I2 is equals to HFE IB. Ooh, that looks familiar because it looks like this. So we can deduce that H21 is equals to HFE. Boop, boop. Okay, now let's I1 equals 0 because we want to do that. Let's erase this. So there's no current going in here. Now, if there's no current going in here, we can immediately say that V1 is equals to HREVC. And VC is technically V2, so we can just say V2. That looks really familiar. It looks like V1 is equals to H12 V2. So H12 is equals to HRE. Now, last part. I2 equals to, what is I2? Well, I2 is equals to V2, because, okay, first thing is IB, this is IB, and there's no current, IB is 0, so this is 0, this is open circuit, so there's no, this is open circuit, so the current really only goes in here. Now, pay attention, because this says Siemens, this is not resistance, this is admittance, so I2 equals V2 times HOE. And we can write it out loud like this. Now, yes, so we can end up deducing H21 equals to, sorry, H12 HOE. Hopefully this makes sense. Two-port networks. Again, H parameters is used a lot in 2133. You will see this again in 2133 and you will have a lot of fun doing it. You can tell a lot about transistor. You can know the feedback constant. You can know the gain, how to find the gain out of the transistors. If there's a resistor going on through here, you can know a lot of stuff. This is a good model for the transistor. Now finally, transmission parameter. Now, transmission parameter, I left this pretty simple for a reason, because we want to save time. Let I2, okay, let me just write down the equations. V1 equals A V2 minus I2B. I1 equals to CV2 minus I2D. We get two equations. So we let I2 equals 0 for now. So what does that mean? That means there's no current going in here. So obviously we know two things. One is we know the input impedance. We know V1 is going to equals, it doesn't really want it, it just wants V2. So we know V2 is going to equals to voltage division of V1, and that is 1.5. So we can deduce that V1 equals 1.5 times V2. Cool. And that tells us that A is 1.5. Next up, what do we need? Let's look at this part and see what we need. We need C, because I2 is 0 right now. C. So V2, we need to express V2 in terms of I1. So V2 times I, it's pretty simple. It's literally just I1 times 20 equals V2, because I2 is 0. So this is I1. I1 times 20 is V2. Pretty simple. Just a regular Ohm's law. You will get V2 I1 equals to 0.05 V2. And you will end up with C equals to 0.05 Siemens. Now let's keep going by letting V2 equals 0. Let V2 equals 0. What does that mean? V2 is 0. That means we short circuit this part. We see nothing but a 10 ohm resistor. Now, by short circuiting this, we know that I2 is going to be equal to negative I1, because no current is going to go through this resistor. So we can safely say that D is going to equals to 1, because there's a negative sign here. Negative cancels out, so this is going to be 1. Underscore this. And what else? We need to find B. So we need to find V1. So V1 is going to be I1 times 10. V1 is going to be I1 times 10, or negative I2 times 10. Doesn't matter, because I1 equals negative I2. So negative I2, ooh, what does that say? That says B equals to 10, because 10 and B matches here. We get our transmission parameter, A, B, C, D, 1.5. A, B is B is 10. C is 0.05 Siemens. D is 1. Cool, everyone. Hopefully you're good. I'm gonna go ahead and copy and paste. Oops, sorry. I'm gonna go ahead and copy and paste this. Now, application is you can cascade transmission parameters like this and multiply them together to get the transmission parameter of the entire system. So let's find this one. Transmission parameter of the following circuit. So we have 3 of these circuit, let me just remove this one, cascaded together, what do we do? Really simple, don't overthink this. You want to have 3 of your, they appear everywhere, I just need to drag them down here. Whoa, 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 calm down, okay. Whoa, okay, sorry, my bad. Okay, I can do this. Ooh, it doesn't really like me, doesn't really like me. Okay. I can do one more. Multiply these 3 matrices together. So you do it one by one. You should first multiply one of them, which will end up with, if you try really hard to do it, you get 2.075 times 0.125. 25 here, 2.5. Is it 25? Yeah, 25. That's 1.5 here. And then multiply with another matrix of yourself, because you just multiply one of them. And you will end up with a final answer of 5.375, 52.5, 2.75, and so transmission parameter is usually used to analyze transmission lines, and you can cascade them like this. It's pretty cool. So you use different parameters for different stuff. Okay, I believe that's the end of my workshop. My crash course for ELSOC. Thanks for watching. I'm sorry that the audio quality is not the best, but hopefully you find this crash course insightful. And yes, see you next time. Goodbye.